So we were talking about kMeans clustering algorithms, where it's motivated from the extensive cost hierarchical clustering. So where we were looking at more improved version of the clustering algorithm. So we went over the main ideas. So where we start by thinking K centroid, these are random centroid, and let's start from here. Where assuming Euclidean distance is used, where this is the data set you have given, and say this is your initial assignment of the centroid. So M1, M2, M3, these are just random points on the data space. So based on that, the first step you want to do is to decide the membership. So for each of these instances, estimate the distance to each of these centroid and find out the closest one, for example, like this. And move on to the next data point and estimate the distance to each of these centroid. Find out the closest one. Next guy, estimate the distance to all of the centroid and find out the closest one, and so on. But if you do so for all of the instances, you will find out the membership. So with data points that are closest to M1 or marked with green, data points closest to M2 marked with red, the rest are orange. And based on this assignment, update your centroid. So centroid is again the mean point for all the cluster members. So by considering all of those green data points, try to find out the new average. For all of those red, find out the new average. For all of these orange, find out the new average. And this new average data points are eventually going to be your new centroid by definition. So M1, M2, M3, they are moving to the new position like this. Oops. So these are updated M1, M2, M3. And based on these new centroids, try to measure the distance from each data point to the new centroid again. So measure the distance to each centroid. And you may notice that this time, for this guy, closest to M2 instead of M1. And you're going to do this for all of these data points. For example, this guy, again, now closer to M3. So this will change your cluster assignment. And next thing you want to do is update the centroid based on the updated assignment. So M1, M2, M3, they are going to move again like this. So basically you are determining the cluster membership and updating the cluster center. And you're doing these two interchangeably. So this is how kMeans algorithm working. And updating these two, you are essentially updating this quantity. So this quantity is called as the sum of squared error, or SSE. So each time you have cluster center and you have cluster membership. So cluster membership xn belongs to Si. S means a cluster. So Mi is the centroid of Si, and we want to find out the best centroid and the best assignment. And based on the notion that we have studied so far, since you have this quantity that estimates sum of squared error, and we also identify that the goal is to minimize this error. The way you do it is simply setting the derivative to 0. So if you calculate the derivative of SSE and set it to 0, you can get how to update your centroid for t+1 iteration. And like we discussed last time, well, kMeans clustering algorithm is guaranteed to converge. So that means well, those MI centroids, they are going to settle somewhere on the data space. So you're simply iterating your algorithm until your centroids are not moving anymore. But moving on to the next slide. So this is a more formalized algorithm. So you initialize all means. So this is centroid. And the first step is assignment step. So assignment step, you're going to decide which SI is best suitable for XN. So XI is cluster, and XN is end data point. And the notation given here is comparing two components, but we'll try to parse this. This is simply minimization. So you want to find out the difference between XN and MI. So you want to decide one of the centroid for XN. That is the smallest among all possible good differences. So there are k different centroid, and you want to measure the difference between XN and all of these centroid. And you want to find it minimum. So this is basically minimization. And after you decide the cluster membership, well, based on the membership that has been set, well, you're updating the centroid, and the stage is equivalent to taking the mean of the cluster members. And step 2 and step 3, it is repeated until converges. So this is basically summarizing what we have discussed. So, well, there are a couple of discussion points, and this is what really makes kMeans clustering algorithm interesting. So the first point that we want to discuss today is distance metric. So kMeans algorithm, well, it does not work if you haven't decided what kind of distance metric should be used. So if any distance metric is not defined, well, kMeans is not applicable. And well, so far the example was given using the notion of Euclidean distance. But this is just for default for many cases, but this is not a must thing. So well, this is not the only answer, and you may consider different distance metric. Well, other thing that is interesting is the notion is slightly tricky, but well, what it means is, say there are two different types of data in one space. And if you want to find out a cluster that looks like this, well, this is something not possible with kMeans. So what it does is, well, each time we are taking the mean of the cluster, and the entire algorithm is driven by the cluster center. But that means we are assuming Gaussian distribution towards the data. So based on this, all the cluster has to be shaped like an ellipsoid. And one of the extended topics from the distance metric is data normalization. So far we haven't talked about the actual values of the data, and we implicitly assuming the scale of the data are equivalent. But if you consider the Euclidean distance, you're going to simply take the summation of the squared difference. And eventually you're going to take the squared root. Well, this is again geometric mean of all data attribute. So while you are taking this mean, one of the attribute has a higher scale or larger scale, then maybe your estimation is dominated by that large attribute. So for example, consider you have a data with 3 different attributes: height, weight, and income. If you consider the reasonable range of these attributes, height should be somewhere between 140 to 200, for example. And weight should be ranging between 40 to 140. But income, well, it has a different digits. So maybe it is somewhere around 20 million or 500 million won. So if you simply put all three attributes to this notation of the distance, maybe your distance metric is dominated by the largest scale. So to avoid this kind of situation, we often normalize the data. And this is almost not an option for most of the existing machine learning model. So data normalization is a step to rescale the data attribute such that different attributes become comparable. And there are two commonly used approaches. One is using mean and standard deviation. So say you have M column, and out of M different attribute, you have jth attribute. So for jth column of your data, first take the mean of that column and take the difference between each individual data point and the mean of that attribute. And you want to divide it by standard deviation on that column. So if you convert all the data value using mean and standard deviation, well, this is something called as standardization. Well, another common way to normalize the data. So again, for each of data attribute, take each observation and subtract using the minimum value from the column. And you divide it by the maximum value of that column, subtracted by the minimum value of that column. So this second method is called as min-max normalization or simply scaling. So if you do the first approach, then your data will be centered around 0. And your standard deviation after normalization becomes 1. If you take the second approach, so min-max scaling, your normalized data will ranging between 0 and 1. So there are two commonly used approaches for normalization. And moving on to other widely discussed approach that is picking k. So we speak about kMeans. So we have k different clusters. So picking up k, we want to find out some of the best cluster out of the data set. And earlier we defined one of the metrics that this is the metric that we are optimizing. That is SSE or sum of squared error. But there is a caveat. So that is if you blindly increase k, sum of squared error will simply going down when you increase the number of clusters. Well, this is clearly observed when you think of one extreme case. So you have n data points. Say you have n data points, and if you define n different cluster on the data set. So say you have 5 data points, and individual data points are defining a cluster. Well, if you do so, cluster center is going to the data point itself. And in this case, sum of squared error becomes 0. So this is obviously the situation that we don't want. So sum of squared error is one of the guidance for us, but this is not an absolute value that we want to optimize. Well, here comes one of the similar scenario. So let's try to illustrate the situation that we just discussed. So this is the data set kTdid and grasshopper data set. So kTdid is in Korean 여치 and grasshopper is 메뚜기. So you're going to compare the length of the antenna and length of the abdomen side. And based on the physical trait of these two properties, you may be able to distinguish catbid and grasshopper. That's the idea. And instead of applying some of the supervised technique, we first want to apply clustering on it. So I don't know how many cluster I need, so I'm starting from one. So everything is belonging to one cluster. And cluster center is simply the mean of all the data points. And if you take the sum of all the differences, so taking the sum of all the differences between centroid and all the data points, the summation will be 873. And k is now increased to 2. And now you have 2 cluster centers. And if you add up all the differences to each of those cluster centers, then sum of squared error becomes 173. Now increase it again to 3. So now you have 3 clusters. And take the summation of all the differences. Where if you do so, the sum of squared error is again decreasing. So you will find it again and again. And it is continuously decreasing to 0 if you have n clusters. But if you draw the trend of this sum of squared error, you're starting from 800 something, and k is increased to 2, it is around 180 something. So there was a rapid decrease from cluster number 1 to 2. But after that, things are sort of slowed down and a little bit settled. So based on this kind of a trend, we often say K2 is highly suggestive from this data set. So by looking at the trend of SSE, sum of squared error, and looking at this kind of angle, this is something called as knee finding or elbow finding technique or heuristic. So heuristic means, it's not mathematically proven algorithm, but this is a technique often works. Works in most cases, this would be better. So this elbow technique is how you set number of cluster K. And earlier we discussed that kMeans algorithm is highly dependent on how you set the initial cluster center. So the kMeans algorithm is sensitive to initialization. And also it is sensitive to outliers. So there are some techniques to avoid this situation. So one is using soft assignment. So soft assignment is where eventually we will study mixture of Gaussian, and mixture of Gaussian is a technique that relaxes kMeans algorithm in some way. So mixture of Gaussian can be thought as a generalization of kMeans. So what this technique does is where you have these data points, and you are sort of assuming there are 2 Gaussian like this. And for each of these data points, you're going to represent each data point as a mixture of 2 Gaussian. So we are going to study this kind of technique later on. Another technique that helps you make kMeans algorithm less sensitive to initialization and also outlier, that is what we have studied last time. So k-midweight algorithm. So instead of means, we are using cluster median. And kMeans algorithm is dependent on the initialization. So there are a bunch of studies how to initialize the cluster center as well. So one of the common technique is using random points as we discussed it. But instead of selecting random points in your data space, you can select a random instance as well. So this is where two commonly used technique. And there is a heuristic like kMeans++, and you can find a detailed description about this algorithm from textbook, chapter 21. Briefly, the idea is where since you have data like this, well, maybe you can pick one of the data points randomly, and your next choice of initialization is one of the data points furthest from your initial point. And the next cluster center that you want to pick is another furthest data point from what you have selected, and so on. So, well, this is asking you to carefully choose initial centroid using existing data points. So there are a bunch of techniques we discussed, but commonly used the most is using multiple runs. So each time you are starting from random centroid and do it again and again, well, K is fixed. Well, this is the important thing. Well, given a fixed K, we want to choose the clustering result that results in the minimum SSE. So we have discussed many things. So we talked about data normalization, distance metric, and how to set K, how to initialize the centroid. Well, all of these things were to have the good set of clusters. And while we are doing that, well, one thing that we should do fundamentally is to have the definition of good clusters. So we have one single metric that is the sum of squared error, but we continuously say, well, this is not a perfect metric. At the same time, to tell the truth, there is no perfect metric for clustering result. So it is an unsupervised approach. So there is no ground truth. Well, based on that, there is no clear definition of the best clusters. But we can roughly say, well, there are two different perspectives. One is internal criterion. The other is external criterion. And internal criterion is evaluating the goodness of a cluster based on the data set itself. So by looking at the data set and also cluster result, where you are evaluating its within cluster, the similarity between data points, they are high. At the same time, between different clusters, the similarity is low. So in this TOEIC example, data are gathered together, and if those data gathered together belong to the same cluster, that's good. But in this case, what you have in the middle, marked with the red, they are crossing between two different data mass. So this is lower intercluster similarity. And also this increases intercluster similarity. And this is obviously the opposite of what we want to have. And along this line, there is one of the metric that is sort of widely used, but at the same time, well, not many people are using this actually. So silhouette score is one of such things. So what it does is basically starting from silhouette coefficient. And this silhouette coefficient is estimated on each individual data sample. So silhouette coefficient SC of nth data instance, that is based on the difference between Bn and An, and that is divided by maximum of Bn and An. And Bn and An is defined in below, so An is the mean distance to the other instance in the same cluster center. So this is intra-cluster similarity. And Bn is inter-cluster similarity, but you're considering only the closest cluster. So where you are belonging to one cluster, and there is another cluster, there is another cluster, For each of these guys, you are considering very next one. So AN is again mean distance within the cluster. BN is the mean distance to the instances in the next door. And based on that, we can sort of assign some meaning. So semantically, AN is approximately representing the compactness of the cluster. So if all the data points they are similar to each other, you can say your cluster is compact. The BN can be estimated as a measure between cluster. So this is actually the minimum distance between the cluster. Well, if you apply this is the difference between BN and AN divided by the maximum of BN and AN. So your silhouette coefficient is ranging between -1 and +1. And it has again some semantic. So when your coefficient is close to 1, your instance is close to all the member within the cluster. So this is good. And far from other cluster, this is again good. But some other cases, when the coefficient is close to 0, that means your instance is close to the cluster boundary. So you have data points like this, and this is your cluster. Where if you have some data point in the middle, where SC may close to 1, but there is some data point in the boundary, SC is going closer to 0. And there are some cases when your coefficient is negative. And if that's the case, you may think the cluster is assigned to a wrong cluster. And so far we discussed the silhouette coefficient. This is defined on each individual data instances. And there is a silhouette score. This is the aggregated version of the silhouette coefficient. So this is the mean silhouette coefficient over all data instances. So, you can try to come up with some other metric that evaluate the goodness of your cluster internally. So you are simply looking at the data and try to evaluate the goodness of the cluster. Well, that's possible. But at the same time, eventually we prefer this kind of external approach. The external approach is simple. You need to have a ground truth information. That means you require labeled data for your analysis. So, for example, in this data set, you have axis and O's. And number of clusters are 3, but still you can clearly make a cut between circle and axis. Or like in the previous case, where if you have a cluster like this, where one of the cluster has a severe mixture of O's and X, and this is something that we don't want to have. So we discussed the many properties of kMeans clustering algorithm, and here comes an example in real life. So kMeans clustering algorithm used a lot in image segmentation. So image segmentation is sort of simplifying your image in multiple blocks of the similar color. So this is your input image. This is simply a photo, and this photo becomes multiple blocks of the same color, like this. And you can try to find the boundary between different colors as well. And here are multiple different examples like this. So on this side, you have your realistic photo, and on this end, some of the good segmentation results. Actually, from the second column to the end, all of these are different segmentation results with different K. So K is smaller when you're starting from the left, and K is larger. And eventually we want to find the sweet spot in terms of K to find the good segmentation. And how it works with the kMeans is relatively simple. So what we want to do is just set K first of all and try to find the clusters of RGB vector of your image. So you are considering each individual pixel one by one and try to perform kMeans on your RGB information. So your pixels will be clustered into one of you have, and eventually you're going to replacing all individual pixels with your cluster centers. So it's going to be a very simplified version of the original image.